Our last topic in this lecture on univariate descriptive statistics is outliers. We've already talked a little bit about outliers informally, but now I want to discuss what you should specifically do about outliers. So, what is an outlier first off? Well, outliers are values that are well separated from most of the data. For example, we've already talked about Bill Gates' income. If everybody in the class makes $100,000 and then Bill Gates enrolls in this class, clearly his income is going to be well separated from the rest of ours. So that is one example of an outlier. We can detect them with box plots, as we've already discussed. So having identified and detected outliers, what do we do about them? Well, the answer to that question depends on another question. So you should ask yourself, why is some value an outlier? There are two possible answers to that question. The two answers are, first, it's a mistake. It's an erroneous value. The other possible answer is that it's a correct but extreme value. So Bill Gates' income would be an example of the second class. So Bill Gates' income is what it is. It's correct and it's extreme. Very often, though, there'll be values that are erroneous, and these can be due to a number of causes. It could be a simple typo. So if you have a 5-point scale, how satisfied are you with your experience at CPK today? The valid values are 1, 2, 3, 4, and 5. If someone is typing it in, perhaps they bump the 6 key while they hit the 5, and you see a number 56. Well, that would be an example of an error. Whenever you have errors, if possible, you want to fix them. So go back to the original survey if it's a paper survey and change that 56 to a 5. Sometimes these will be deliberate sabotage. So if you go back to that number of times example, there were people who claimed to have dined at California Pizza Kitchen or was it other casual dining restaurants 99 times in 30 days. Well, that seems pretty unlikely. Either that's deliberate falsification where they're just making up numbers, or they misread the question and wrote a big value. In either case, it's a mistake. So if you can fix such values, do so. Otherwise, set them to missing, which means that they're going to get excluded from analyses. Now, let me show you how you do that in SPSS. So let's go back to SPSS for a moment. And remember, we had some issues with the age variable. So there were a lot of erroneous values with that. There were zeros and twos and threes, and then there was those 99s. Let's start by running some descriptives on this variable. So let's go into descriptives, and we'll go to explore. This will give us a pretty complete range of descriptives on it. And I'm going to hit OK. So now we've got a complete range of descriptives on that age variable. And what we'll see is that there are 24,975, so all observations are populated with an age. And you get some pretty strange values. So the minimum was 0, the maximum was 99. So how would we set all of these values that are outside of the acceptable values to missing? The answer lies in the recode statement. So we're going to go up to transform, and then we're going to go to recode. Let's see, transcode, all right, recode. We want to recode into a different variable. Now, this menu I find slightly confusing. We're going to bring age in, and then we need to transform it to a new variable. I'm going to call it age 2. It's always a good idea to create a new variable rather than overwrite the original variable, because sometimes you want to transform the original variable differently at some point. And so let's say age without bad values is good for a label. Now the thing students always forget to do is they forget to hit change. You got to hit change. And so age is now going to get transformed into age 2 is the way to read this. Go click on old and new values. So I'm going to specify a range now, a range of all acceptable values. So these are supposed to be adults. therefore all values 18 through, I'm going to say 80. Now, remember, there was nobody between the ages of 80 and 98. Then you had that big spike of 99s, and I think the 99s are erroneous. So any value between 18 and 80 I'm going to regard as a valid value. So we're going to copy it. So just hit copy, and then you have to hit add. So 18 through 80 is just going to be copied. All other values will be set to system missing. So I'll go add that. Go hit continue and go hit OK. Now, if we go back to the data set, what you'll see is a new variable that takes the original age whenever the original age is valid, and then in instances such as row 15 that have an age of 0, this age 2 is system missing. I'm going to rerun now the explore module on this. So let's get age out of there, and we're going to copy age 2 in. Go hit OK. And now what you'll see is that there are only 22,480 valid cases. So we've dropped all of those values that were 0 and 99, and the minimum is 18, the maximum is 79 now. So it looks like it did exactly what we wanted it to do. All right, so my point with all of this is that if you have mistakes, like those zeros and the 99s, you want to set them to system missing if there's no other way to fix them. Perhaps the harder case is when it's a correct but extreme value. So what do you do then? Well, there are a couple possibilities, and we've already talked about some of these. So again, you have to understand why that value is so extreme. Sometimes it comes from another segment. So for example, you'll probably use the popcorn factory data next quarter. And if you look at the popcorn factory data, so they sell popcorn to consumers and other organizations, you're going to find that there are a lot of outliers in that data set in terms of the amount that they've spent in the past, say, 2 years. The reason for those outliers is that some of them are businesses. So who else would be buying hundreds of canisters of popcorn in a year? So it's probably a business sending out popcorn to its best customers or something. All right, so if the observations come from an identifiably different group like businesses, separate them out. And you've got one group of businesses and another group of consumers. When that's not the case, when they don't come from an identifiably different population, you often want to reduce the influence of these outliers. So we already saw how Bill Gates' income could inflate the income of everybody else. Now there are two approaches to this. Either we use robust statistics. So we've already met a lot of robust statistics. The median, the interquartile range, the trimmed mean are all robust statistics. The main benefit of these is that they maintain the original units. So if you get rid of some, if you use a trimmed mean, the units are still dollars as opposed to some transformed version of that. The alternative is to transform the variable, and we've already seen examples of this as well. So we can, for example, take the log or even the square root of a variable. And the problem with using a transformed variable is that now you're not talking about dollars, you're talking about log dollars. But sometimes this is okay because there are examples where it makes sense to think on such log scales. For example, the Richter scale is on a log scale. Another possibility that survey researchers use all the time is they just avoid outliers in the first place. And they do so with response buckets. So for example, on the California Pizza Kitchen survey, we saw a question where it asked you to check off 1 to 5 times, 6 to 10, all the way through 21 plus. So anybody who wants to be an outlier would check that 21 plus bucket, and they're really no longer an outlier. They're just in that 5th bucket. All right, so you need to think very carefully about what you're going to do with a variable. We have a couple of cases to help you think through this. So I want you to work through the Chapter 4 case, the case of the suspicious customer, which is here in the course packet, also in the book, for next time. And that'll give you some practice with these concepts and to do the homework exercise for this week where we're going to see that logging certain variables makes sense.